A very warm welcome to all of you. Myself, Professor Nagarese from Department of Chemistry, KG Somaya College, Kopargaon. In this lecture, we are going to take the second lecture on the chapter Nuclear Chemistry, in which we have to study the stability of the nucleus, in which we are going to study the different factors affecting the stability of the nucleus. What are that different factors? So that we have to study one by one. Before starting this lecture, please subscribe my YouTube channel and press the bell icon in order to get the notification for the upcoming video lectures on important topics. So let's start this lecture. So first of all, the stability of the nucleus is considered. So we have to look towards what is meant by the stability of the nucleus and what are the different factors which are responsible for this type of the stability. Now, as far as the composition of the nucleus is considered, this very small part of a nucleus consists of the number of protons and number of neutrons. We know very well that the protons having the positive charge and neutrons having the negative charge. Now, as far as these protons are to be considered having a positive charge, so within a very small region of a nucleus, number of protons are there having a similar charge. We know that the similar charges having the repulsion among them. So how in this very small region number of protons remains and the nucleus is stable in nature. So this type of the stability of the nucleus having some supportive parameters for its stability. So we have to study all these parameters or factors which makes the nucleus stable. The stability of the nucleus can be considered in terms of the following factors. So these four important factors we have to study. First one is nature of nuclear forces. Second is the odd-even combinations of protons and neutrons. The third one is neutron to proton ratio of nucleus. And the fourth one is binding energy and average binding energy. So let's start the first factor among these four. The first factor is the nature of nuclear forces. The nucleus consists of proton and neutron. The following three interactions are given by the proton and neutrons present in a nucleus. That interactions are proton-proton interaction, proton-neutron interaction, and third one is neutron-neutron interactions. These interactions are of attractive types and force arising from them operate within the nucleus only, so they are called as the short-range forces. The proton-proton interactions are partly attractive and partly repulsive. Their magnitudes are high within the nucleus. Now, as far as this first parameter is to be considered, so this parameter depends upon the type of interactions present in the nucleus in between the protons and neutrons. So these three interactions are possible. These interactions are of attractive types. These interactions are operative within the nucleus only, and that's why all these three interactions are called as the short range forces. These interactions are no doubt partly attractive as well as the partly repulsive. Only one interaction, that is a proton-proton interaction, shows both the nature, that is partly attractive and partly repulsive, while the remaining two are only partly, or they are only attractive type of interactions. Now their magnitudes are high within the nucleus only. Outside the nucleus their magnitudes are negligible. So this is the first important parameter which affect the stability of the nucleus. The second important factor is odd-even combinations of protons and neutrons. How the proton and neutron numbers combine together in order to form the stable nuclei. So this we have to study in this parameter. There are 274 stable nuclides in nature. In nature, as far as the number of stable nuclides are to be considered, they are equal to the 274. The stability of these nuclides can be studied by considering the odd-even combinations of protons and neutrons. Now, how these 274 nuclides can be occur in a nature depending upon different combinations of protons and neutrons. So that we have to study from this data in this table. Now, in this table we have to consider number of protons, number of neutrons, their mass number, the number of stable isotopes and their examples. Now, as far as the even number of protons and even number of neutrons are to be considered, they having the mass number, even mass number. So 165 stable isotopes are to be there belonging to this first combination of even protons and even number of neutrons. So most of the isotopes belongs to this first combination or this first type. The simple examples of nuclei or isotopes are, first one is a helium with atomic number 2 and mass number 4. The carbon nuclei is there, oxygen nuclei is there. So we can say that near about 80% of the nuclei occur in the nature made up from this type of the combination. There is a even number of protons and even number of neutrons having a mass number again even. The second combination of protons and neutrons is a even number of protons and odd number of neutrons with odd mass number having 55 stable isotopes in the nature. The examples are oxygen nuclei with atomic number 8, mass number 17, and second one is a neon nuclei with atomic number 10, mass number 21. The third combination is odd proton number and even number of neutrons having odd mass number. So 50 stable isotopes of nuclei is occur in a nature. For example, lithium nuclei with atomic number 3, mass number 7, and sodium nuclei. And the last one is odd number of protons and odd number of neutrons with even mass number having a very small number, that is a 4. So these three nuclei are there, and this is a second important factor. The third important factor which affects the stability of the nuclei is neutron-proton ratio, that is N by Z ratio. Now, how this neutron-proton ratio affects the stability of the nuclei? The stable nuclei of high light elements up to atomic number 20 shows neutron-proton ratio equal to 1. Next to atomic number 20, neutron-proton ratio is greater than 1. The nuclei having neutron-proton ratio between 1 to 1.536 lies in stability strip. So these are the three important conclusions from this neutron-proton ratio. Now, to understand these concepts, we have to consider one graph of number of neutrons versus number of protons. So if we plot such a type of the graphs, we get such a type of the region in this graph. This is one strip is there. Now this strip is called as the stability strip. So this graph gives us a three different areas. One is called as the center region, that is a stability strip. One region to the left hand side of this stability strip, and third one is to the right hand side of this stability strip. So we have to consider these three regions for stability of the nuclei. Those nuclei which are present in this stability strip are called as the stable nuclei. Those nuclei which are present at the bottom of this stability strip having the neutron-proton ratio equal to 1, and they are called as the highly stable nuclei. Again, those nuclei are present within this stability strip region. They have the neutron-proton ratio in between the 1 to 1.536. They all are called as the stable nuclei. So we can say that this region is called as the stability strip. Now, those nuclei which are occur on the left hand side of this nuclei, suppose this X nuclei is there, which have the neutron-proton ratio greater than 1.536, are called as the highly unstable in nature. On the same instant, those nuclei which are occur on the right hand side on this stability strip, suppose this is the next nuclei, Y nuclei is there, it has the neutron-proton ratio less than 1. So both these nuclei are called as highly unstable. They want to become stable by entering into this stability region. First of all, we have to study how this X entered in this stability strip, initially having the neutron-proton ratio greater than that of the 1.536. So what happens? In this nuclei, the neutron number get converted into the protons with the emission of the beta particle, and due to which what happens, this neutron-proton ratio initially is greater than that of the 1.536, but due to the conversion of these neutrons into protons, this ratio is converted in between to that of the 1 to 1.536, and that's why this X enters in this stability strip, and that's why this X becomes stable nuclei. On the other hand, the Y nuclei, which having the neutron-proton ratio less than 1, it want to become stable by converting this ratio in between 1 to 1.536. So this is possible by the conversion of these protons into neutron with the emission of the positrons, or it may be done with the help of electron capture, and due to which this Y nuclei again get converted into the or get entered in the stability strip. So we can say that those nuclei which are present in this stability strip are called as the highly stable nuclei, while those are occur on the either side of this stability strip are called as the highly unstable nuclei. These highly unstable nuclei may get converted into the stability strip depending upon the conversion of neutrons into protons or conversion of protons into neutrons with the emission of the beta particle or with the emission of the positrons, or it may be emission of the electron capture is there. So this is one important parameter, neutron-proton ratio, for the stability of the nuclei. The next important factor which affects the stability of the nuclei is called as the stability of the nucleus in terms of the binding energy. The binding energy of a nucleus gives the information about how strongly nucleons are held in the nucleus. So this binding energy is very much important as far as the stability of the nuclei is to be considered. Now, what is the binding energy? It is the amount of energy which must be supplied to the nucleus so as to break it into its constituent particles. So whenever we want to break a particular nuclei into its constituent particles, then the amount of energy which is required is called as the binding energy. The next important concept is a mass defect. It is denoted by the delta M. It is the difference between the theoretical mass and atomic mass of a nucleus. Now, this theoretical mass is to be calculated with the help of number of protons present in the nuclei multiplied by their mass number plus number of neutrons multiplied by the mass of a neutrons. So this is a theoretical mass. Once we know the theoretical mass, from which the mass defect, that is a delta M, can be calculated as mass defect, that is a delta M, is equal to M dash minus M, where M dash is called as the theoretical mass while M is called as the atomic mass. Once we know this mass defect, from this we can easily calculate the one energy, that is a binding energy. So binding energy of a nuclei is equal to mass defect multiplied by 931.1 million electron volt. Now, how to calculate the binding energy of a nuclei? So for this purpose, just consider here a simple example of helium nuclei. The atomic mass of this helium nuclei is equal to 4.0026. This helium nuclei consists of the 2 protons and 2 neutrons, from which we can easily calculate the calculated mass. It is calculated as M dash is equal to 2 into mass of a proton plus 2 into mass of neutrons. If we substitute the constant values of mass of protons and mass of neutrons, we get here calculated mass of helium as 4.0320 atomic mass unit, from which we can calculate the mass defect, that is equal to delta M equal to M dash minus M. If we substitute the values of M dash and M, we get here mass defect equal to 0.0294 atomic mass unit, and from this mass defect we can easily calculate the binding energy, that is equal to 931.1 into mass defect, and from which we get the value of binding energy equal to 27.36 million electron volt. So this is a very simple steps for calculations of binding energies there. Now, the next important concept within this binding energy is called as the average binding energy, that's E bar. It is defined as the ratio of binding energy of a nucleus to its mass number, which is given by E bar is equal to E by A. So if we take such a type of the ratio of binding energy to that of the mass of a nucleus, it is called as the average binding energy of a nuclei. Now, this average binding energy of a nuclei is very much important in order to get the stability of a nuclei. So if we plot a graph of average binding energy per nucleon versus the mass number, we get such a type of the nature in a graph in which we get the different regions. So depending upon that, we can classify the nuclei as, depending upon this mass number, the nuclei are classified as light nuclei, medium nuclei, heavy nuclides and unstable heavy nuclides. Now, depending upon the average binding energy per nucleon, these nucleons having a different stability. Those nuclei which are occur between this mass number 60 to that of the mass number 120 are called as a highly stable nuclei. So this region is called as the maximum stability region. Some nuclei having the highest stability. So these are the some selected nuclei. Nuclei A, B, C, D up to this G is there. So these nuclei having a different stability. If we compare nuclei A to that of the B, this A nuclei having the more average binding energy per nucleon. So it is a more stable as compared to this of the B. So from this graphical nature, we can easily find out the stability of the nuclei, or we can compare the stability of the nuclei. Now, as we go with the mass number more than 120, gradually this atomic average binding energy per nucleon gradually going on decreasing. So we can say that to the heavy nuclides or to the more than atom mass number 120, the nuclei having a very small average or very less average binding energy as compared to this mass number 60 to 120 nuclei. And so the heavy nucleides are called as the unstable nuclei. So from this average binding energy per nucleon, we can say that as the average binding energy per nucleon has the more value, naturally the stability of the nuclei is more. So this is a very important factor for considering the stability of the nuclei. The next important point in this same concept, that is packing fraction. So this packing fraction is given by the equation packing fraction is equal to atomic mass minus mass number divided by mass number multiplied by the 10,000. So if we solve this simple equation, we get the packing fraction of a nuclei. Now from this packing fraction, we get an idea regarding the stability of the nucleus. The negative packing fraction indicates the stability of the nucleus. So if the packing fraction having the negative value, that nuclei is called as the highly stable nuclei. The positive packing fraction indicates instability of the nucleus, while the heavy element shows positive packing fraction and hence are unstable in nature. So this packing fraction gives us an idea regarding the stability of the nuclei. Whether the packing fraction is negative or positive, we get the respective type of conclusions from this packing fraction. So in this lecture, we focus upon the very important topic of the nuclei, that is the stability of the nuclei and the factors affecting the stability of the nuclei. We consider here the four different factors which affect the stability of the nuclei. The first one is the nature of nuclear forces. Second one is the odd even combinations of protons and neutrons. Third one is neutron proton ratio, and the fourth one is the binding energy and average binding energy. This is a very important topic in order to consider the stability of the nuclei. So within a very short time span, we focus the important aspects of all these four factors. So I hope you understand these four different parameters which affect the stability of the nucleons or nuclei. The remaining points from this chapter we will take in an upcoming lecture. So with this, I stop here. Thank you so much.